That's an English sentence typed into an LLM chat box. Watch the robot. One sentence just became a multi-stop mission, and notice what the robot does with it. It takes the whole plan and sequences it itself, while a model on Amazon Bedrock rides along and narrates. That'll take a while to drive, so I'll leave it running and come back to it. I'm Drew Malekia, Principal Engineer and Architect at VividCloud. We build cloud robotics and physical AI systems on AWS. A word about what you're looking at. This is a working system, not a mock-up. A simulated NVIDIA Nova Carter and Isaac Sim on a GPU workstation, streaming the simulator's own render. Every reading that robot produces is moving through AWS as we speak and landing in a data lake. The panel down here is running SQL against it. Nothing on the screen is canned. But the console is the least interesting thing on my screen. It's one face of something underneath, and that something is what I actually came to talk about. The trouble with leading with an architecture is that architectures are abstract until someone builds a business on one. So let's do it the other way around. Before we come back to this robot, I want to walk you through 5 completely unrelated companies, different industries, different customers, different economics. And I want you holding one question the whole way through. What do these have in common? First business. Somebody inspects things for a living. Bridges, warehouses, insurance claims. Today that's a person with a clipboard and a camera, and the cost per inspection is a day of somebody's time. Here's what it looks like when a robot does the walking. Every frame it captures gets scored by several specialists at once. Recognition to identify what kind of asset is in frame. Lookout for vision to raise a hand at anomalies nothing specifically trained it on. And a purpose-built SageMaker endpoint to grade severity. Step functions arbitrate the votes. Moderate finding, it pauses the mission and sends the robot back for a closer look. Severe, it pages a human. Every frame, every score, every decision persists so a person can audit it later. The property that makes this a business and not a science project, no single model gets to decide. Ensemble, then escalation with a human at the top. Hold that one in your head. Now take the machine learning out entirely because the next business doesn't have a model in it anywhere. Second business, a completely different industry. A survey firm turning captured imagery into 3D deliverables. Their problem isn't AI, it's compute economics. Hours of GPU a few times a week, which is the single worst kind of hardware to own. So, the robot drives a capture route. Greengrass Stream Manager pushes gigabytes into S3 as resumable multi-part uploads, designed for connectivity that comes and goes. A manifest lambda turns the upload into a job spec. Step functions submit it to AWS Deadline Cloud, which spins up a GPU worker fleet running open drone map, and it scales back down to 0. A textured mesh and orthomosaic land in S3 so you can open in the browser. Render Farm is a service for robots. Different industry, different math, different services doing the work. So, an inspection company and a survey firm. So far nothing in common but a robot. The third one doesn't care about images at all. Third business, somebody who operates a fleet rather than builds one, and whose worst day is unplanned downtime. The premise here is more interesting than the architecture. Per sensor thresholds miss the failures that actually cost money. A bearing about to seize doesn't look dramatic on any single channel. It shows up as a shift in the relationship between vibration, motor current, and temperature. So lookout for equipment learns the joint signature of a healthy operation and scores every frame against it. TimeStream drives the live fleet health board, and when the score drifts, Bedrock reads the recent window and writes the work order in plain English. Which signals moved, since when, and what it thinks is going on. The on-call engineer gets a paragraph to context instead of an anomaly score at 3 in the morning. That's the whole product. 3 businesses, 3 completely different middles. The fourth one is about the moment autonomy runs out of ideas. Fourth, somebody selling remote operation. Because autonomy is the default, but every fielded robot eventually meets a situation a human should own. 2 lanes, video out through Kinesis video streams, running continuously whether anyone is watching or not. Sub-second, glass to glass once an operator joins, peer-to-peer WebRTC after the signaling handshake. Cognito decides who may watch. Then control back in, and this is the part I'd point out. The joystick returns through the same gateway the language model uses. Human control inherits identical auth, identical signing, identical audit trail, and a handoff trigger watches the autonomy stack so a stuck robot opens a ticket instead of waiting to be noticed. 4 businesses, an inspection company, a survey firm, a fleet operator, a teleop provider. Different customers, different services, different unit economics, nothing obviously shared. There's a 5th in that menu and I'm saving it. It's the best one. So, what do these have in common? This is our demo pipeline. Every one of those four is this diagram with a different middle. 2 lanes. On top, the data plane, telemetry moving out of a robot towards storage. Underneath, the control plane, commands moving in. Same architecture, opposite directions. And 3 zones, which is the actual idea of this video. Edge, the robot and whatever runs beside it. Ingestion, the AWS services that buffer, transform, and route. Storage and analytics, where data lands so something useful can happen to it. Every cloud robotic systems we build has that same topology. What changes between them is which boxes sit in the zones. What doesn't change is the zones. Let me trace one message so it's concrete. A robot publishes odometry on a ROS topic at 50 Hz. A Greengrass component on the same machine subscribes to it. Greengrass being the AWS Edge runtime, which is how cloud services end up running on a robot without the robot needing the internet to keep functioning. It publishes to IoT Core over MQTT, and IoT Core fans it out. One copy to a dashboard, one through Firehose into Parquet and S3, cataloged by Glue, queryable in Athena. Roughly a third of a second to the screen, roughly a minute to being SQL. Note the branch below the spine. Imagery never touches the broker. Camera binaries go edge direct to S3. A metadata row goes through an IoT rule into DynamoDB so they stay findable. Structured telemetry takes MQTT, bulk bytes take S3, and each transport does the job it's actually good at. Get that boundary wrong, and your bandwidth bill and your latency both go sideways at the same time. Now the control plane. A human types or a model does. It goes through a gateway, Amazon Bedrock AgentCore to a Lambda. The gateway exists to keep the model away from the tools. The model asks, the gateway executes under scoped IAM after authenticating the caller. The Lambda publishes to a command topic, Greengrass on the robot picks it up, hands it to Ross, and the robot moves. The model holds no AWS credentials. It calls tools the way a person would, and every command traces an identified principal in CloudWatch permanently. Agentic control stops being a governance argument and becomes an audit trail. One more thing about this page. Those numbers are live. Messages per second, broker state, age of the last message, active topics. This isn't a picture of our architecture. It's a monitor of the one that's running right now. And here's the claim that makes those 4 businesses interesting instead of just varied. The middle of this diagram is the same every time. The edge shifts a little, different robot, different drivers, different topic names. The right hand shifts a lot because that's where your business problem lives, and your business problem is nobody else's. But IoT Core, Firehose, S3, Glue, the gateway, the identity model, that's very nearly a copy on each project. Most of the engineering hours is in the first build lived there, almost none in the second. 4 wildly different businesses, one shared middle. That's the argument. Now let's go back to the console because I've barely shown you what it does. Still going. There's the mission, written out. Storage A arrived, pauses after where it grabbed a camera frame, and then on the last leg to the loading dock. That's the robot's own navigation status, round-tripping through AWS and back into this browser, the whole time I was showing you diagrams. Now, I want to be careful what I'm claiming here because some of you have spent years on robot control and yours is more sophisticated than mine. Our command vocabulary is deliberately basic. It's a demo. The interesting part was never what we tell the robot to do, it's where the model sits. The chat commands at the level of intent, a destination, a sequence, a goal, and the robot's own mission server sequences it from there, which means the model is in the planning loop, never the control loop. It doesn't steer. Model latency isn't inside the robot's control cycle. A model outage isn't a robot without a plan, and command leaving AWS reaches the robot's mission server in about 1.5 seconds. That's the arrangement and makes the answer to would you put a language model in front of that machine a yes. And it holds no matter how sophisticated the controller on the other end is. Yours plugs in where ours is. 2 other things this window does, briefly. It can see. The model reads the actual camera frame rather than inferring the room from coordinates. Those 2 picture-in-pictures are the same feeds it gets. And it can query the business, not just the robot. That question goes to Athena, an operator asking how the fleet did today, and the operator driving the robot are in the same window. Nobody leaves the console to go learn a query editor. The rest of the screen is instrumentation, and 2 panels are doing more than they look. The 3D view on the right isn't drawing our robot's world. It's the raw scene itself, the map, both nav2 cost maps, the live plan, the laser scan. When that path bends around the rack, you're watching the planner change its mind. And the data lake panel at the bottom is Athena. Distance, runtime, waypoints reached, times it got stuck, rows landed, those numbers went up during the drive you just watched. Which means the thing nobody plans for and everybody eventually wants has been happening quietly this whole time. The training corpus is assembling itself. Every drive, sim or reel, with pointers to the camera frames, catalog and queryable indefinitely. Not because anybody chartered a data initiative, because the pipe was designed right on day one. Which brings me to the fifth business. The fifth one is the one I saved, and it's the one this whole architecture is really for. Somebody's product is the model, and their problem is the model only improves from operating data they have no way to capture, label, train on, and ship back. The left column is the ingest you've now watched work. Storage drops you into a ring, and that ring is SageMaker. Ground truth for labeling and curation, distributed training, a model registry so you always know what shipped, inference endpoints, governance, human review, and automated evals gating promotion, and monitoring for drift, which feeds the next round of labeling. It's a flywheel because it doesn't stop. What a vision language action training job wants is a mission ID, a frame index, the action taken, an S3 pointer to the frame, and the plain English instruction that produced the trajectory. Intent tied to observation, tied to action. The lake carries the telemetry and the frame pointers today, pairing the instruction to the trajectory, lands with the loop, which is the real argument for designing the loop before you collect the data. That field is nearly free at capture time and brutal to reconstruct later. Inference exit the ring on the right, through a lambda, back through Greengrass, back onto the robot. And here's the thing. The development path is Greengrass, the same over-the-air update mechanism. So when a model version clears governance, a lambda packages it as a component revision, Greengrass pushes it down to the fleet, robot pulls it and loads it, and then runs its next missions on the new model. And that data comes back in through the ingest column on the left. The loop doesn't stop at the cloud boundary. It runs out to the machine and back, which means this isn't a training loop, it's a development loop. And training, deploying, testing stop being phases in a plan and become three things that happen on every turn of the same wheel. Every operating hour compounds. And back home it goes. So, 5 businesses. An inspection company that needed several models to disagree with before it trusted one. Survey firm that needed GPU farm for hours a week that didn't want to own it, a fleet operator who needed a paragraph instead of an anomaly score, a teleop provider who needed a human to inherit a robot's exact permissions, and a robotics company whose product is a model that only gets better from the data it hasn't collected yet. 5 industries, 5 completely different right-hand sides, one architecture underneath all of them. 3 zones, telemetry out, commands in, identity model that holds for a person and a language model equally, which is the thing I'd actually like to leave you with. The dashboard is a face, and faces are cheap. The 5 use cases are the interesting half of your problem, and they're yours, not ours. What we do is the part in between. The layer shows up in every one of these conversations. Getting it right once means every robot you deploy after that starts further along. If something you saw resonates with a problem you've been sitting with, that's the conversation we like having. Thank you.